Have you ever stopped to truly think about what space and time actually are? Not just as abstract ideas, but as the very fabric of reality, the invisible framework that holds everything together. Close your eyes for a moment and picture this. You're floating in the vast emptiness between galaxies, where distances are so immense that light itself takes millions of years to cross them. Time here doesn't tick like a clock. It stretches and warps, bending around stars and black holes like a river flowing over rocks. This isn't science fiction, it's the universe as we understand it today, and the deeper we look, the more mysterious it becomes. For centuries, humans have tried to unravel the secrets of space and time, from ancient astronomers mapping the stars to Einstein, rewriting the rules of reality with his theory of relativity. Yet, even now, these concepts defy our intuition. How can space expand faster than light? Why does time slow down when you're moving at incredible speeds? And what does it mean that the past, present, and future might all exist simultaneously? These aren't just philosophical questions, they're the cutting edge of modern physics, where the answers could reshape everything we know about existence itself. In this video, we're going on a journey to the heart of these mysteries. We'll explore how Einstein's ideas revolutionized our understanding of gravity and motion, how quantum mechanics throws everything into chaos at the smallest scales, and why some scientists believe there might be hidden dimensions woven into the fabric of space. Along the way, we'll confront paradoxes that twist the mind, like black holes where time stands still and quantum particles that seem to communicate faster than light. By the end, you won't just see space and time as background elements of the universe. You'll see them as the main characters in the greatest story ever told. So let's dive in and start peeling back the layers of reality, one astonishing discovery at a time. When you look up at the night sky, it's easy to think of space as nothing more than a vast, empty expanse, a silent void between stars. But the truth is far stranger. Space isn't just a passive backdrop. It's an active participant in the universe's grand drama. Picture it like the surface of a trampoline. Place a bowling ball in the center, and the fabric stretches and bends under its weight. Now imagine that bowling ball is a star, and the trampoline is space itself. That's the essence of Einstein's revolutionary insight. Massive objects don't just sit in space, they shape it, warping the very fabric around them. This curvature is what we experience as gravity, the invisible force that keeps planets in orbit and galaxies bound together. But the story doesn't end there. At the tiniest scales, quantum physics paints an even wilder picture. Space might not be smooth and continuous like we once thought. Instead, it could be a frothy, turbulent sea of fleeting particles and energy fluctuations, popping in and out of existence in fractions of a second. Some theories suggest space is woven from unimaginably small strings, vibrating at different frequencies like the notes on a cosmic guitar. Others propose a foamy structure, where microscopic bubbles of spacetime constantly form and dissolve. These ideas might sound like science fiction, but they're serious attempts to explain why the universe behaves the way it does at its most fundamental level. Even the so-called empty space between galaxies isn't truly empty. It's buzzing with energy, dark energy to be precise, a mysterious force causing the universe to expand faster and faster. Then there's quantum fields, invisible webs of potential that fill every corner of reality, waiting to spark particles into existence. Think of space as an ocean, with waves of energy rolling through it, unseen currents tugging at matter, and hidden depths we're only beginning to explore. The more we learn, the clearer it becomes. Space isn't just where things happen. It's a dynamic, living thing full of secrets waiting to be uncovered. Time slips through our fingers like sand, always moving forward, or so it seems. But what if time's relentless march is just an illusion? Ancient Greek philosophers wrestled with this puzzle, debating whether time was a river flowing in one direction or a cycle repeating endlessly. Fast forward to the early 20th century, and Einstein turned everything upside down with his theory of relativity. He showed that time isn't a fixed, universal clock ticking the same for everyone. Instead, it's elastic, stretching and compressing depending on how fast you're moving or how close you are to a massive object like a planet or a black hole. Imagine two identical clocks, one placed on a mountaintop, the other at sea level. Over time, the lower clock actually ticks slower because gravity's pull warps time itself. This isn't science fiction. It's been proven with incredibly precise atomic clocks, but the strangeness doesn't stop there. Some physicists argue that time might not even exist as a fundamental part of the universe. Think about a movie reel. The frames are all there at once, but we experience them one after another. Similarly, the block universe theory suggests that past, present, and future are equally real, frozen in a four-dimensional tapestry where every moment exists simultaneously. Our brains just stitch them together into a linear story. This idea challenges our deepest intuitions. How can the future already be out there if we haven't lived it yet? Yet quantum experiments hint at eerie connections between particles that seem to ignore time altogether, as if cause and effect aren't as rigid as we thought. Then there's the mystery of time's arrow. Why does time move forward, not backward? The answer might lie in entropy, the universe's tendency toward disorder. A shattered glass never reassembles itself because entropy increases over time, creating a one-way street for events. But here's the twist: the laws of physics work just as well if time runs backward. So why don't we see broken cups spontaneously mend or smoke pour back into a candle? Some scientists speculate that the Big Bang set the initial low entropy conditions that made time's arrow possible. Others wonder if multiple arrows of time could exist in other corners of the cosmos, where cause and effect run in reverse. Time dilation adds another layer of wonder. Astronauts aboard the International Space Station age slightly slower than people on Earth because they're moving at nearly 18,000 miles per hour. At everyday speeds, the difference is negligible, but near light speed, time bends dramatically. A traveler racing toward a distant star and back might return to find Earth centuries older while they've barely aged. This isn't hypothetical. GPS satellites have to account for these tiny time shifts to keep our maps accurate. Time, it seems, is far more malleable than our daily experience suggests. So is time real or just a trick of perception? The debate rages on. Some theories, like loop quantum gravity, suggest time might emerge from deeper, timeless building blocks, like temperature arising from the motion of atoms. Others propose that consciousness itself stitches moments together, creating the illusion of flow. Whatever the truth, one thing's certain: time's elusive nature keeps pushing the boundaries of human understanding, revealing a universe far stranger and more wondrous than we ever imagined. Einstein's vision of spacetime wasn't just a tweak to physics, it was a complete rewrite of reality's rulebook. Before him, space was thought of as a rigid, unchanging grid, and time as a steady, universal metronome ticking the same for everyone. But in 1905, his special theory of relativity shattered those assumptions, revealing that space and time are deeply intertwined, like threads in a cosmic tapestry. Then, 10 years later, general relativity took it even further, showing that this fabric isn't just connected, it's dynamic, warping and bending under the weight of matter and energy. Picture a bowling ball placed on a stretched rubber sheet. The heavier the ball, the deeper the dent it creates. Now replace the ball with a star and the sheet with spacetime itself. That's gravity in Einstein's universe, not some mysterious force yanking objects together, but the natural result of matter shaping the geometry of reality. Planets orbit stars not because they're being pulled, but because they're rolling along the curves carved into spacetime like marbles spiraling around a funnel. Even light, which has no mass, bends as it travels through these warped regions, a phenomenon famously confirmed during a solar eclipse in 1919 when stars near the Sun appeared slightly out of place. But how does this curvature actually work? Think of spacetime as a flexible, four-dimensional fabric, 3 dimensions of space and 1 of time where every event leaves a mark. A speeding rocket, a collapsing star, even the Earth orbiting the Sun, they all create ripples and dips in this fabric, influencing how objects move and how time flows. Near a black hole where spacetime is stretched to its limits, the distortion is so extreme that time slows to a crawl, and light can't escape at all. Yet here's the mind-bending part. These aren't just abstract concepts. GPS satellites orbiting Earth have to account for these tiny spacetime wrinkles, adjusting their clocks to stay in sync with the ground. Without relativity, your phone's navigation would be off by miles within minutes. Einstein's equations also predicted something even wilder: gravitational waves. Imagine tossing a pebble into a pond and watching the ripples spread. Now replace the pebble with 2 colliding black holes and the pond with spacetime itself. In 2015, scientists detected these ripples for the first time, a century after Einstein theorized them, proving that spacetime isn't just curved, it can vibrate, sending whispers of cosmic collisions across the universe. The beauty of general relativity is how it unites the cosmic and the everyday. The same math that describes the birth of the universe in the Big Bang also explains why an apple falls from a tree or why clocks tick slower on a mountaintop than at sea level. Spacetime isn't just a static stage, it's an active player, responding to the actors while also shaping their performance. And yet, for all its elegance, Einstein's masterpiece clashes violently with another pillar of physics: quantum mechanics, leaving scientists still searching for a theory that can reconcile the two. But that's a story for another time. For now, let's just marvel at the audacity of a single idea rewriting our place in the cosmos, revealing a universe far more interconnected and dynamic than we ever dreamed. Light speed isn't just a number, it's the universe's ironclad rule, a boundary woven into the fabric of reality itself. Imagine you're in a starship accelerating faster and faster, pushing toward that glittering speed limit of 186,000 miles per second. At first, everything seems normal, but as you inch closer, strange things start happening. Time stretches like taffy, your watch ticks slower than clocks back on Earth, and the space around you contracts, squeezing distances like an accordion. This isn't science fiction, it's Einstein's special relativity in action, revealing a cosmos where speed warps the very nature of time and space. Take the famous twin paradox. One twin stays on Earth while the other rockets off at near light speed. When the traveling twin returns, they've aged only a few years, while their Earth-bound sibling might be decades older. How? Because motion isn't just movement through space, it's movement through spacetime. The faster you go, the more your journey through time slows down, a phenomenon called time dilation. Atomic clocks on fast-moving jets have confirmed this. Time literally ticks slower for them than for clocks on the ground. The real shocker is why light speed is unbreakable. It's not that we lack the technology, it's that the universe won't allow it. As an object speeds up, its mass balloons, requiring infinite energy to reach light speed. But light itself doesn't experience time or distance. For a photon, the moment it's emitted is the same moment it's absorbed, even if it's traveled billions of years across the cosmos. This constancy of light speed reshapes our intuition. If you're racing toward a beam of light, it still moves away from you at the same speed as if you were standing still. Could anything cheat this cosmic rule? Quantum entanglement seems to defy it, with particles instantly influencing each other across vast distances. But no information is actually transmitted faster than light. It's more like a synchronized dance where the steps are predetermined. Wormholes, hypothetical shortcuts through spacetime, might offer a loophole, but they'd require exotic matter with negative energy, something we've never observed. Even the expansion of the universe can outpace light speed, but that's space itself stretching, not objects moving through it. So why does light get to set the speed limit? Because it's not just light, it's causality itself. Light speed is the rate at which cause and effect propagate, the universe's way of preserving order. Without it, events could happen in reverse, breaking the chain of reality as we know it. The speed of light isn't just a barrier, it's the glue holding the cosmos together, ensuring that time flows forward and stars shine in a sky we can still reach for, even if we can't outtrace their light. Black holes aren't just objects in space, they're cosmic whirlpools where the very rules of reality unravel. Imagine standing at the edge of a black hole's event horizon, the point of no return. From your perspective, time slows to a crawl, stretching seconds into eternities, while the black hole's immense gravity tugs at every atom in your body. But here's the twist: for someone watching from afar, you'd appear frozen in time, like a figure trapped in a photograph, never quite crossing over. This eerie phenomenon isn't magic, it's space-time bending so severely that light itself can't escape, warping perception in ways that defy common sense. Dive deeper and things get even stranger. At the heart of a black hole lies the singularity, a point where density becomes infinite and space-time curves into a knot so tight that Einstein's equations break down entirely. Picture crushing the entire mass of a star into a space smaller than an atom, a place where gravity wins its ultimate victory, crushing matter into oblivion. But what happens there, no one knows for sure. The laws of physics as we understand them simply stop working, leaving scientists to speculate about quantum foam, alternate dimensions, or even gateways to other universes. Yet black holes aren't entirely dark mysteries. Thanks to Stephen Hawking, we now know they can slowly evaporate, leaking energy in the form of Hawking radiation. Imagine a pair of particles popping into existence near the event horizon. One falls in while the other escapes, stealing a tiny bit of the black hole's mass over eons. Given enough time, trillions upon trillions of years, even the mightiest black hole could vanish in a whisper of particles, a ghostly farewell to a cosmic titan. Perhaps the most mind-bending idea of all is the holographic principle, which suggests that all the information swallowed by a black hole isn't lost but encoded on its surface, like a cosmic hard drive storing data in 2 dimensions instead of 3. Think of it like a movie projected onto a screen. The images appear 3-dimensional, but they're really just flat patterns of light. If this principle holds, it could mean reality itself operates like a hologram, with black holes serving as clues to a deeper, more fundamental layer of the universe. So are black holes cosmic trash compactors, or could they be portals to something unimaginable? Some theories propose that inside a black hole's singularity, space-time might twist into a tunnel, a wormhole connecting distant regions of the cosmos or even other universes. Others argue they're the end of the line where space-time itself is torn apart. One thing's certain, black holes force us to confront the limits of human knowledge, revealing just how much we still have to learn about the fabric of existence. They're not just voids in space, they're windows into the unknown, challenging us to rethink everything we thought we knew about time, space, and reality itself. If you could shrink down to the smallest possible scale, far smaller than an atom, space itself might look nothing like the smooth, empty void we imagine. Instead, you'd find a turbulent, seething ocean, a quantum foam where reality flickers in and out of existence like bubbles in a boiling pot. This isn't just poetic imagery, it's a radical prediction of quantum mechanics, suggesting that at distances a trillion times smaller than a proton, spacetime becomes a chaotic dance of energy and particles. Think of it like looking at the surface of a calm lake from a distance. It appears glassy and still, but zoom in close enough and you'll see tiny ripples, splashes, and disturbances. Quantum foam is like those ripples, but for spacetime itself. Here, particles and antiparticles spontaneously emerge from nothingness, borrowing energy from the universe for the briefest moments before annihilating each other. These virtual particles aren't just theoretical, their effects have been measured in labs, like the Casimir effect, where two metal plates placed incredibly close together feel a subtle push from the particles popping into existence around them. Even stranger is the idea of zero-point energy, the notion that empty space isn't empty at all. Instead, it's a buzzing hive of minimum energy, a background hum that never fades, even at absolute zero temperature. Picture a guitar string that never stops vibrating, no matter how gently you try to quiet it. This energy is so fundamental that some theories suggest it could be the source of dark energy, the mysterious force accelerating the universe's expansion. But the real puzzle is gravity. In Einstein's universe, spacetime is smooth and continuous, bending gracefully under the weight of stars and galaxies. Yet in the quantum foam, spacetime is a frenzied, jittery mess. How can these two wildly different pictures coexist? Some scientists believe the answer lies in the foam itself, that if we could understand its structure, we might finally bridge the gap between quantum mechanics and general relativity, creating a theory of everything. One daring idea is that spacetime isn't fundamental at all, but emerges from something deeper, like the way temperature arises from the motion of atoms. Imagine a pixelated image. Up close, you see individual dots, but from afar, they blend into a smooth picture. Could spacetime be the same, a collective illusion of something more basic? Theories like loop quantum gravity propose that spacetime is woven from tiny, indivisible loops, while string theory suggests it's built from vibrating strings in higher dimensions. The quantum foam might also hold clues to black holes and the birth of the universe. If spacetime can fluctuate so violently at tiny scales, could it create microscopic wormholes or even new universes? Some models suggest that the Big Bang itself might have been a quantum fluctuation in a larger multiverse, where universes bubble up like foam in an infinite cosmic ocean. Of course, testing these ideas is a monumental challenge. The scales involved are so small that even our most powerful particle colliders can't probe them directly. But experiments with ultra-precise lasers, gravitational wave detectors, and even quantum computers are inching us closer to answers. Whether quantum foam is the key to unification or just another stepping stone, one thing's clear: the fabric of space is far richer, stranger, and more dynamic than we ever dreamed. It's a reminder that reality, at its core, is anything but ordinary. Time travel has been a staple of science fiction for over a century, from H.G. Wells' classic novel to blockbuster films, but could it ever be more than just a story? Surprisingly, Einstein's equations don't rule it out. They allow for something called closed time-like curves, paths through spacetime that loop back on themselves, creating a bridge between the past and future. Picture a roller coaster that twists so sharply it doubles back, letting you revisit the same point in time. While this sounds like pure fantasy, the math checks out. The catch: you'd need conditions so extreme they border on the impossible, like negative energy or a black hole spinning at nearly the speed of light. One of the most tantalizing possibilities involves wormhole shortcuts through spacetime predicted by general relativity. Imagine folding a piece of paper so two distant points touch, then poking a hole through them. In theory, a wormhole could connect not just different places but different times. The problem: wormholes would likely collapse instantly unless stabilized by exotic matter with repulsive gravity, something we've never observed. Even if they existed, traveling through one might require speeds faster than light or expose you to forces that would shred atoms. Then there's the infamous grandfather paradox. If you went back in time and prevented your grandparents from meeting, how could you exist to make the trip in the first place? Some physicists argue the universe would self-correct, creating a new timeline where your actions don't erase your own existence, a concept called the many worlds interpretation. Others suggest nature would conspire to stop you, like a mysterious force jamming your time machine's controls just as you're about to meddle with history. Quantum experiments add another layer of weirdness. Particles in labs have shown behavior that looks like they're influencing their own past, a phenomenon called retrocausality. It's not quite time travel, but it hints that cause and effect might not be as rigid as we thought. The universe, it seems, has a few tricks up its sleeve when it comes to the arrow of time. So is time travel possible? The laws of physics don't outright forbid it, but the hurdles are staggering. Even if we cracked the technical challenges, the philosophical questions remain. Would altering the past unravel reality, or are multiple timelines branching endlessly like strands of a cosmic web? For now, time travel stays firmly in the realm of theory, but in a universe as strange as ours, who's to say what's truly impossible? 13.8 billion years ago, the universe as we know it burst into existence not in some vast, empty space, but as space itself. The Big Bang wasn't an explosion in the conventional sense. It was the sudden, violent expansion of space-time, matter, and energy from a single point of infinite density called a singularity. Picture a balloon inflating from a tiny speck to the size of a galaxy in a fraction of a second. Except the balloon is reality itself, and the speck contains everything that would ever exist. But here's the twist: the Big Bang didn't happen at a specific location in space. It happened everywhere at once because back then, everywhere was the same point. In those first unimaginable moments, the universe underwent a period called cosmic inflation, expanding faster than the speed of light. This wasn't matter flying outward. It was space stretching, carrying matter along for the ride. Inflation explains why the cosmos appears so uniform today, with galaxies scattered evenly across the sky like dots on a balloon. But what triggered it? Some theories suggest a quantum fluctuation in a pre-existing void, a tiny blip of energy that ballooned into everything we see. Others propose a collision between higher dimensional membranes in a multiverse, a cosmic accident birthing our reality. Then there's the haunting question: what came before? The word before might not even make sense if time itself began at the Big Bang. Imagine asking what's north of the North Pole. The concept breaks down. Yet some models, like loop quantum cosmology, suggest the singularity might have been a bounce, the remnants of a previous universe collapsing before rebounding into ours. Others speculate about a timeless, eternal multiverse where universes bubble up endlessly, each with its own laws of physics. The Big Bang also left behind clues like the cosmic microwave background, the faint afterglow of the universe's fiery infancy. This ancient light, detected by telescopes as a whisper of radiation, is a snapshot of the cosmos at just 380,000 years old. Its subtle ripples hint at quantum fluctuations stretched to cosmic scales during inflation, seeds that grew into galaxies and galactic clusters. But the most mind-bending idea is that the Big Bang might not be unique. If inflation can happen once, why not Chinese letter? Some theories posit an infinite inflationary sea, where universes sprout like bubbles in boiling water, each with its own version of spacetime, particles, and even dimensions. In this vast multiverse, our universe could be one of countless others, some with physics so alien they're unrecognizable. So did spacetime have a true beginning, or is it part of an endless cycle? The answer might lie in the marriage of quantum mechanics and gravity, a theory still out of reach. For now, the Big Bang remains the ultimate origin story, not just of stars and planets, but of space and time themselves, unfolding from a mystery we're only beginning to unravel. In the late 1990s, astronomers made a discovery that turned cosmology on its head. They found that the universe isn't just expanding, it's accelerating, as if some invisible force were pushing galaxies apart faster and faster over time. This mysterious driver, dubbed dark energy, makes up about 68% of the cosmos, yet we still have no idea what it actually is. Imagine blowing up a balloon with tiny dots on its surface, representing galaxies. Instead of the dots slowly drifting apart as the balloon inflates, they suddenly start racing away from each other, as if the balloon were being stretched by unseen hands. That's the unsettling reality we live in, a cosmos where space itself is being stretched apart at an ever-increasing rate. The leading explanation for dark energy comes straight from Einstein's playbook, though he initially dismissed it as his greatest blunder. He called it the cosmological constant, a kind of energy woven into the fabric of space itself. Picture empty space not as nothingness, but as a seething ocean of quantum activity, where particles flicker in and out of existence. This quantum froth might generate a repulsive force pushing space apart. But here's the problem. When scientists calculate how much energy this quantum vacuum should produce, the numbers are off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in the history of physics. Some theories suggest dark energy isn't constant at all but evolves over time, growing stronger or weaker. Others propose it's a new kind of field, similar to the Higgs field that gives particles mass, but with bizarre repulsive properties. Then there's the chilling possibility of the Big Rip, a scenario where dark energy grows so powerful it doesn't just push galaxies apart but tears atoms, space-time, and even the fabric of reality itself to shreds. Imagine a universe where, billions of years from now, stars vanish as their light can no longer reach us, then planets are ripped from their orbits, and finally, the very molecules in your body are pulled apart in a cosmic crescendo of destruction. Yet dark energy's dominance raises deeper questions. Why does it only kick in now, after billions of years of slower expansion? Is it a fundamental property of space, or could it be a sign that our understanding of gravity is incomplete? Some scientists even speculate that dark energy might be a shadow of extra dimensions, a ripple from hidden layers of reality we can't perceive. The truth is, dark energy isn't just another puzzle, it's a glaring clue that our picture of the universe is missing something profound. And until we solve it, the cosmos will keep accelerating into the unknown, carrying us along for the ride. We take for granted that space has 3 dimensions: length, width, and height, but what if reality is far roomier than it appears? String theory, one of the most ambitious frameworks in physics, suggests that the universe might be hiding extra dimensions, curled up so tightly they're invisible to us, like the folds of a crumpled piece of paper too tiny to see. Imagine an ant walking along a telephone wire. From a distance, the wire looks one-dimensional, but up close, the ant can circle its surface, revealing a hidden second dimension. In the same way, our universe might be threaded with microscopic loops and twists, dimensions beyond the three we experience every day. These extra dimensions aren't just abstract math. They could solve one of physics' biggest puzzles: why gravity is so weak compared to the other fundamental forces. Picture gravity as a force that leaks into these hidden dimensions, diluting its strength in our observable world. It's like water seeping through the pores of a sponge. What we feel as gravity might just be the leftover trickle. This idea, called the brainworld scenario, suggests our entire universe could be a three-dimensional brain floating in a higher dimensional space, with gravity as the only force able to escape it. The shapes of these hidden dimensions matter, too. String theorists study intricate geometries called Calabi-Yau manifolds, six-dimensional twists and knots that could determine everything from particle properties to the number of forces in nature. Think of them as the cosmic equivalent of a flute's shape defining the notes it can play. If these manifolds vibrate in just the right way, they might explain why we have electrons, quarks, and photons, all dancing to the tune of hidden dimensions. But how could we ever detect something so small? Some experiments hunt for signs of extra dimensions in particle colliders, searching for energy that suddenly vanishes, perhaps slipping into another dimension. Others look for deviations in gravity at microscopic scales, where its true strength might peek through. And if these dimensions exist, they could open the door to wild possibilities, like parallel universes hovering millimeters away from us, separated by folds in spacetime we can't yet perceive. String theory's extra dimensions remain speculative, but they offer a breathtaking vision that the fabric of reality is richer and more layered than we ever imagined. Whether they're the key to unifying physics or a beautiful dead end, one thing's certain: the universe still has secrets tucked away in corners we're only beginning to explore. What if everything you see around you, the stars, the planets, even your own hands, is nothing more than an incredibly detailed projection, like a cosmic illusion? This isn't the plot of a sci-fi movie. It's a serious theory gaining traction in physics called the Holographic Principle. The idea is as mind-bending as it sounds. Our three-dimensional universe, with all its depth and complexity, might actually be encoded on a two-dimensional surface somewhere at the edge of reality, like a movie stored on a DVD. The screen we're watching, that's the universe itself, a vast hologram where every event, every particle, is just information painted onto a hidden canvas. The roots of this idea trace back to black holes, those cosmic enigmas where gravity crushes matter into oblivion. When something falls into a black hole, it's gone forever, or so we thought. In the 1970s, physicist Jacob Bekenstein made a startling discovery. Black holes have entropy, a measure of disorder, and it's proportional to the area of their event horizons, not their volume. This was bizarre. In everyday life, entropy depends on how much stuff you have. Think of a messy room where more objects mean more chaos. But black holes suggest the information about what falls into them isn't lost. It's smeared across their surfaces like ink on a page. Stephen Hawking later showed that black holes slowly evaporate, raising a paradox. If the information inside them disappears, it violates quantum mechanics' rule that information can't be destroyed. The solution: maybe the information was never inside the black hole to begin with. It was always on the surface, encoded in tiny Planck-sized pixels. This led physicists like Leonard Susskind and Gerard T. Hooft to a radical idea. If black holes store information on their boundaries, maybe the entire universe does too. Imagine a soap bubble. The soap film is a two-dimensional surface, but it encloses a three-dimensional space. Now scale that up to cosmic proportions. The universe's entire contents, every galaxy, every atom, could be written onto a distant, invisible boundary like a celestial hard drive. We're not just talking about a metaphor here. The math suggests that the equations governing physics in a three-dimensional space can be perfectly mirrored by equations operating on a two-dimensional surface, with no loss of information. It's as if the universe is a video game rendering a 3D world from 2D code, and we're the characters living inside it. Quantum entanglement adds another layer of intrigue. When particles become entangled, their properties link instantaneously across vast distances, defying classical notions of space and time. Some researchers argue this spooky connection makes sense if reality is fundamentally two-dimensional, with entanglement acting like threads stitching the hologram together. Picture a tapestry. From the front, you see a rich, detailed image, but flip it over, and you'll find a tangled network of threads. In this view, entanglement is the hidden stitching holding the universe's projection in place. So what would it mean if the holographic principle is true? For starters, space and time might not be fundamental. They could emerge from something deeper, like pixels forming an image. This could bridge the chasm between quantum mechanics and gravity, two theories that refuse to play nice. In a holographic universe, gravity might not be a force but a side effect of information processing, like lag in a computer simulation. Even stranger, it could imply that our perception of free will is an illusion, with every choice already written into the cosmic code. Skeptics point out that testing this idea is notoriously difficult. The hypothetical two-dimensional surface encoding our reality would exist at the universe's edge, far beyond our observable horizon. But some experiments, like precise measurements of quantum noise or gravitational waves, might one day reveal subtle fingerprints of holography. Others look for anomalies in the cosmic microwave background, the afterglow of the Big Bang, which could bear imprints of a pixelated universe. Whether the holographic principle holds up or not, it forces us to confront profound questions about the nature of reality. Are we living in a shadow play, our lives and memories just data on some unfathomable surface? Or is the universe more like a self-portrait, painting itself into existence one quantum pixel at a time? The answers, if they come, might rewrite not just physics but our very understanding of what it means to exist. If you've ever watched cream swirl into coffee or seen a shattered glass scatter across the floor, you've witnessed entropy in action, the universe's relentless march toward disorder. But here's the twist. This isn't just about messy rooms or melting ice cubes. Entropy might hold the key to one of physics' deepest mysteries: why time flows forward at all. Think about it. We remember yesterday, not tomorrow. Eggs scramble but never unscramble. The past feels fixed while the future stays wide open. This one-way street we call time isn't just a human quirk. It's woven into the fabric of reality itself, and entropy is the thread that stitches it all together. The story begins with a 19th-century physicist named Ludwig Boltzmann, who realized that entropy isn't just randomness, it's about probability. Imagine a deck of cards fresh from the box, perfectly ordered. Shuffle it once and it's slightly messy. Shuffle it 100 times and the cards become chaotic. But here's the catch. There's only one way for the deck to be perfectly ordered, and countless ways for it to be disordered. The universe works the same way. Particles start in tidy arrangements like the dense, hot soup of the Big Bang, and over eons, they spread out, seeking every possible configuration. That's why time has an arrow, because disorder is statistically inevitable, a cosmic roll of the dice favoring chaos over order. But Boltzmann's ideas led to a bizarre paradox. If entropy always increases, why did the universe start with such low entropy in the first place? Why wasn't it always a mess? This is where cosmology collides with thermodynamics. Some theorists argue the Big Bang set the initial conditions, like winding up a clock spring, storing order that's been unwinding ever since. Others propose a wilder idea, that our universe is just a random fluctuation in an otherwise chaotic multiverse. Picture an ocean where most waves are tiny ripples, but occasionally, a freak wave crests high enough to create a pocket of order. A Boltzmann brain, a self-aware entity that pops into existence by sheer chance, complete with false memories of a past. If that sounds unsettling, don't worry. The odds of such a fluctuation are astronomically low, but the fact that it's even possible shakes our understanding of reality. Now, what if entropy isn't universal? Could other corners of the cosmos have time running backward? The laws of physics don't care if time flows forward or backward. Equations work just as well either way. But we never see smoke pour back into a cigarette or coffee unmix itself. The difference is entropy's grip on our local patch of the universe. Some speculate that in a hypothetical, anti-universe on the other side of the Big Bang, time might run in reverse, with entropy decreasing as particles rewind toward order. It's a haunting idea, a mirror cosmos where cause and effect flip and our future is someone else's past. Yet entropy's arrow isn't just about physics, it's tied to our very existence. Stars shine because they convert ordered nuclear fuel into disordered heat and light. Life thrives by harnessing energy gradients, feeding on pockets of order to delay the inevitable decay. Even consciousness might rely on entropy's one-way flow, with memories forming as brain states march irreversibly toward higher disorder. In a way, we're all temporary eddies in the cosmic river of entropy, riding its current until it dissolves us back into the void. So is the arrow of time written into the universe's DNA, or is it just a fleeting quirk of our corner of reality? The answer might lie in the quantum realm, where particles sometimes seem to defy time's flow, or in the holographic principle, where time emerges from deeper, timeless layers. Whatever the truth, entropy reminds us that time's flow isn't just a clock ticking, it's the universe telling its story, one irreversible moment at a time. Wormholes sound like something straight out of a sci-fi blockbuster, tunnels burrowing through the fabric of spacetime, connecting distant corners of the cosmos in the blink of an eye. But these cosmic shortcuts aren't just fantasy, they're rooted in Einstein's equations. Back in 1935, Albert Einstein and Nathan Rosen discovered that general relativity allows for structures now called Einstein-Rosen bridges, mathematical shortcuts linking two black holes. Picture folding a piece of paper so 2 points touch, then poking a hole through them. In theory, a wormhole could let you step from one side of the universe to the other without crossing the vast distance in between. But here's the catch: wormholes, as described by Einstein's math, would be catastrophically unstable. The moment you tried to pass through, the tunnel would snap shut like a rubber band, crushing anything inside. To keep a wormhole open, you'd need something truly bizarre: exotic matter with negative energy density. Unlike normal matter, which gravity pulls, exotic matter would repel, acting as a kind of anti-gravity to prop the wormhole's throat open. Sounds impossible, right? Surprisingly, quantum mechanics offers a glimmer of hope. The Casimir effect, where two metal plates in a vacuum experience a slight push from quantum fluctuations, hints that negative energy might exist in tiny amounts. The problem: stabilizing a traversable wormhole could require more negative energy than exists in the entire observable universe. Even if we cracked the exotic matter puzzle, wormholes come with other headaches. Time dilation near their mouths could mean entering one side would strand you centuries in the past or future relative to the other end. Then there's the potential for feedback loops. Imagine a stray photon bouncing through the wormhole, gaining energy with each pass until it explodes into a lethal beam. And let's not forget the grandfather paradox. If you could travel back in time via wormhole, what stops you from accidentally erasing your own existence? Some theories suggest quantum mechanics might enforce consistency, twisting events so your actions can't create contradictions, like a cosmic safety net. Could nature have already crafted wormholes without us noticing? Some speculate that microscopic wormholes flicker in and out of existence in the quantum foam, the turbulent spacetime at the smallest scales. Others theorize that primordial wormholes, forged in the extreme conditions of the early universe, might have stretched to cosmic sizes during inflation, lurking unseen in today's cosmos. A wilder idea posits that black holes could disguise wormhole entrances, with their singularities acting as gateways rather than dead ends. The real question isn't just whether wormholes exist, but whether they could ever be more than mathematical curiosities. Without exotic matter, they remain tantalizing mirages. Yet the mere possibility ignites our imagination. What if we could step through a celestial doorway, crossing light years in an instant? Until science catches up to speculation, wormholes remind us that the universe's rulebook still has pages we've barely begun to read. What if our universe is just one page in an infinite cosmic library, where every possible variation of reality exists simultaneously? The multiverse theory proposes exactly that, a vast, perhaps endless, collection of universes, each with its own unique laws of physics, constants, and even versions of you. Take the concept of bubble universes, for instance. Imagine the early universe as a boiling pot of water, with bubbles constantly forming and popping. In this cosmic foam, each bubble could be a separate universe, inflated by its own Big Bang, forever drifting beyond our observable horizon. Some might contain stars and planets like ours, while others could be barren voids or realms where gravity repels instead of attracts. Then there's the quantum multiverse, where every decision, every random quantum event splits reality into branching timelines. Picture standing at a crossroads. In one universe, you turn left, in another, you turn right. But it's not just about choices. Even the decay of a single atom could spawn divergent worlds. This many worlds interpretation, proposed by physicist Hugh Everett, suggests there's a universe where the dinosaurs never went extinct, where Napoleon won at Waterloo, or where you're reading this script upside down. It's a dizzying thought, infinite versions of history unfolding in parallel, like a cosmic choose-your-own-adventure book where every path is taken. String theory adds another layer, proposing a multiverse where universes exist as membranes floating in higher dimensional space, occasionally colliding like sheets in the wind. These collisions could even trigger new Big Bangs, birthing fresh cosmoses with entirely different rules. Some might have extra dimensions we can't perceive, or forces stronger than our nuclear interactions. Others could be so alien that matter as we know it never forms. But how could we ever detect these shadow realms? Some scientists hunt for bruises in the cosmic microwave background, anomalies that might mark where our universe bumped into another. Others look for strange gravitational effects or particles that flicker in and out of existence, as if slipping between dimensions. The truth is, the multiverse might forever remain untestable, a tantalizing idea just beyond the edge of science. Yet the implications are profound. If every possible outcome exists somewhere, does free will vanish? Are we just one thread in an infinite tapestry of selves? Whether the multiverse is real or not, it challenges us to rethink our place in the cosmos, not as the center of everything, but as one fleeting possibility in a sea of infinite realities. Imagine two coins flipped simultaneously on opposite sides of the galaxy. Yet no matter how far apart they are, they always land on matching sides. This isn't just a thought experiment. It's the bizarre reality of quantum entanglement, where particles become so deeply linked that measuring one instantly determines the state of its partner, even if they're light years apart. Einstein famously dismissed this as spooky action at a distance, refusing to believe the universe could operate in such a seemingly illogical way. But decades of experiments have proven him wrong, revealing a cosmos where connections defy the speed of light and space itself might be an illusion. At the heart of this mystery is non-locality, the idea that objects can influence each other without any physical link or signal passing between them. Think of it like a pair of magical dice. No matter how far you separate them, rolling one to show a 3 guarantees the other will also land on 3. In the quantum world, entangled particles behave this way with properties like spin or polarization. The moment you measure one, its twin snaps into a corresponding state, as if they're sharing a hidden conversation faster than light could ever travel. The real breakthrough came with physicist John Bell's theorem in the 1960s. Bell devised a mathematical way to test whether entanglement could be explained by hidden variables, secret instructions the particles carry from the moment they're created. If the universe were purely local, as Einstein believed, there'd be limits to how correlated measurements could be. But when scientists ran Bell's experiments, the results shattered those limits. Particles consistently coordinated in ways that no classical theory could explain, proving that quantum connections aren't just random, they're fundamentally non-local. So how does this work? One radical interpretation is that space isn't the ultimate framework of reality. Instead, entanglement might reveal a deeper layer where distance is meaningless, a cosmic web of relationships that transcends spacetime entirely. Picture the universe as a vast network, with every particle holding invisible threads that tie it to others, weaving a tapestry of instant connection. This challenges not just our intuition but the very foundation of physics, suggesting that separateness might be an illusion. Quantum entanglement isn't just a laboratory curiosity. It's the engine behind emerging technologies like quantum computing and ultra-secure communication. By harnessing these spooky links, scientists can create networks where information is teleported across distances or computations are performed at unimaginable speeds. Yet the deeper implications are philosophical. If particles can communicate instantaneously across cosmic distances, what does that say about the nature of reality? Are we part of a universe where everything is subtly, invisibly intertwined? The answers might rewrite not just physics but our understanding of existence itself. Empty space isn't what it seems. Reach out and grab a handful of nothing, or at least what you think is nothing, and quantum physics will tell you that your empty hand is actually buzzing with invisible activity. According to quantum field theory, a vacuum isn't truly empty. It's a seething ocean of virtual particles popping in and out of existence so fast we can't see them. These fleeting particles borrow energy from the universe, exist for fractions of a second, then vanish again like bubbles in a boiling pot. This isn't just theoretical, it's been proven in labs and the effects are measurable. Take the Casimir effect, one of the strangest demonstrations of quantum nothingness. Imagine two metal plates placed incredibly close together in a vacuum, just a few nanometers apart. Classical physics would say nothing should happen, but in reality, the plates are gently pushed toward each other. Why? Because the space outside the plates is filled with more of those virtual particles than the narrow gap between them. The outside pressure is greater, creating a tiny but measurable force. It's as if the universe's empty space is alive with unseen energy, pressing in from all sides. Then there's zero-point energy, the idea that even at absolute zero, the coldest possible temperature where all motion should stop, space still hums with residual energy. Picture a guitar string that can never quite settle. No matter how carefully you mute it, there's always a faint vibration. In quantum terms, this means particles never fully rest. They're always jittering, a phenomenon confirmed by experiments with ultra-cold atoms. Some theories even suggest this zero-point energy could be the source of dark energy, the mysterious force accelerating the universe's expansion. But here's the real shocker. This quantum vacuum might hold the key to spacetime itself. If empty space is a dynamic, energy-filled medium, could it be the foundation of reality? Some physicists speculate that spacetime emerges from the interactions of these quantum fields, like waves rising from the sea. Others propose that gravity itself might be a side effect of vacuum fluctuations, a kind of cosmic friction in the quantum foam. So is true nothingness even possible? The answer seems to be no. Every cubic centimeter of empty space, from the void between galaxies to the gaps between atoms, is a storm of potential. What we call nothing might actually be the most important something in the universe, the hidden stage on which all of reality plays out. In the quiet pre-dawn hours of September 14, 2015, a ripple passed through Earth, so tiny it stretched the planet by less than the width of an atomic nucleus. Yet this faint tremor, detected by the Laser Interferometer Gravitational Wave Observatory, or LIGO, marked one of the greatest discoveries in modern science, the first direct detection of gravitational waves. These weren't ordinary waves like those on an ocean. They were distortions in spacetime itself, generated over 1 billion years ago when two black holes, each about 30 times the mass of our Sun, spiraled into each other and merged in a cataclysmic collision. The energy released in that final second was greater than all the stars in the observable universe shining combined, but by the time those ripples reached us, they'd faded to a whisper, a cosmic echo confirming Einstein's century-old prophecy. Einstein's theory of general relativity predicted that massive objects warping spacetime wouldn't just create static curves, they could generate waves like a boat moving across a lake. But even he doubted we'd ever detect them. The distortions were simply too minuscule, requiring instruments sensitive enough to measure changes 1,000 times smaller than a proton. LIGO achieved this with twin detectors in Louisiana and Washington, each featuring laser beams traveling down 2.5 mile long vacuum tubes. When a gravitational wave passes, it subtly alters the length of one tube relative to the other, shifting the laser beams out of sync. The precision is staggering. It's like measuring the distance to Alpha Centauri, the nearest star system, down to the width of a human hair. What makes these waves so revolutionary is how they let us hear the universe. Traditional telescopes capture light, but gravitational waves carry information from events invisible to light, like black holes merging in perfect darkness. The signal LIGO caught wasn't just proof of waves, it revealed details about the black hole's masses, spins, and even the final moments of their violent dance. Since then, dozens more detections have followed, including collisions of neutron stars that also flared up in gamma rays and visible light, giving us a multi-messenger view of cosmic catastrophes. But the implications go far beyond black holes. Gravitational waves could help solve mysteries like the nature of dark matter or the universe's expansion rate. Some theories suggest primordial waves from the Big Bang itself might still be rippling through spacetime, carrying clues about the universe's birth. Future observatories like the space-based LISA mission will detect lower frequency waves from supermassive black holes, potentially uncovering hidden chapters of cosmic history. Imagine living in a silent world, then suddenly gaining the ability to hear. That's what gravitational waves have given us, a new sense to explore the cosmos. They're not just confirming Einstein, they're rewriting astronomy, turning spacetime itself into a medium for storytelling, where every ripple carries the signature of distant, unimaginable violence. And this is just the beginning. As detectors grow more sensitive, who knows what whispers from the dark will decode next? Right now, as you watch this video, you're experiencing what feels like an undeniable present moment, the now. But here's the unsettling truth. Your now might not be the same as someone else's. Einstein's theory of relativity shattered the idea of a universal present, revealing that time isn't a single, steady river flowing the same for everyone. Instead, it's more like a network of streams, each moving at different speeds depending on how fast you're moving or how close you are to gravity's pull. Picture two astronauts passing each other in space at near light speed. For one, a flash of light might seem simultaneous with a distant event, while for the other, it happens noticeably later. Neither is wrong, their nows are simply different slices of spacetime. This phenomenon, called the relativity of simultaneity, means there's no cosmic clock synchronizing the universe. What you perceive as the present moment could be someone else's past or future, depending on your motion or position. Think of it like standing in a crowded stadium. The sound of a singer's voice reaches people at different times based on where they're seated. In the cosmic arena, light and information act the same way, creating a patchwork of nows across the universe. Even Earth's gravity subtly warps time, so a clock on a mountaintop ticks infinitesimally faster than one at sea level. These differences are tiny in daily life, but they add up over cosmic distances or near extreme objects like black holes, where time stretches like taffy. Philosophers have wrestled with this for centuries. Is the present just a fleeting illusion, a trick of consciousness stitching together moments like frames in a film? Some theories, like presentism, argue that only the present is real, the past is gone, the future unborn. But relativity complicates this, suggesting that past, present, and future might all coexist in a static, block universe, where time is just another dimension, like length or width. In this view, your life is like a loaf of bread, with every moment birth, this second, your last breath, existing simultaneously. The flow of time, just how your brain navigates the slices. Quantum mechanics adds another layer of weirdness. At the smallest scales, particles don't seem to experience time linearly. Entangled particles react instantaneously across distances, as if time isn't a factor, while quantum systems can evolve backward under certain conditions. Some interpretations even suggest that observation itself might collapse quantum possibilities into a single now, raising the spine-tingling question: does consciousness play a role in creating the present? So is now real? The answer might depend on who or where you're asking. For a photon racing at light speed, time doesn't pass at all. Its entire existence is a single frozen moment. For us, anchored in gravity and moving at human speeds, the present feels concrete, a shared anchor in the chaos. Yet the universe keeps its secrets, reminding us that reality is far stranger than our senses can grasp. The present might be the only moment we truly inhabit, but it's also the one that slips through our fingers the instant we try to hold it. What if space isn't smooth and continuous like a blank sheet of paper, but more like a finely woven tapestry, a fabric stitched together from billions of tiny, indivisible threads? That's the bold idea at the heart of loop quantum gravity, a radical alternative to string theory that reimagines spacetime as a dynamic network of microscopic loops. Forget the idea of empty space as a void. In this framework, reality is built from interwoven strands so small that if you enlarged one to the thickness of a human hair, an entire atom would dwarf the observable universe. These loops don't just float aimlessly, they connect at nodes, forming intricate structures called spin networks. Picture a cosmic mesh where each intersection hums with quantum information, like a three-dimensional spiderweb vibrating with energy. The key insight: space itself is quantized, meaning it comes in discrete, indivisible chunks. Just as a digital photo breaks down into pixels, space-time dissolves into these fundamental units at the tiniest scales. This has wild implications. There's no such thing as infinite smallness. Try to divide space into ever smaller pieces, and you'll eventually hit a limit, a smallest possible volume, about 10 to the power of -35 cubic meters. One of loop quantum gravity's most stunning revelations is how it handles black holes and the Big Bang. In Einstein's Relativity, these are singularities points where space-time curvature becomes infinite and physics breaks down. But in the loop quantum universe, singularities vanish. Instead, when matter collapses under gravity, it reaches a maximum density and then rebounds like a spring compressed to its limit. Some theorists argue this could mean the Big Bang wasn't the absolute beginning but a big bounce, the aftermath of a previous universe's collapse. Imagine a cosmic phoenix rising again and again from its own ashes. The math behind this is as elegant as it is complex. Spin networks evolve over time, their connections updating in discrete steps, creating what's called spin foam, a four-dimensional structure representing spacetime's quantum history. Think of it as a flipbook where each page is a snapshot of the universe's geometry, and flipping through them shows time passing. Unlike the smooth, deterministic flow of classical physics, time here jumps in tiny, irreducible increments, like the ticking of a quantum clock. But how does this mesh with our everyday experience of space as seamless and continuous? It's all about scale. Just as water feels smooth to the touch despite being made of molecules, space-time appears continuous because these quantum loops are unimaginably tiny. Even the most sensitive instruments can't detect their granularity, yet some experiments hunting for quantum gravity effects, like subtle shifts in high-energy gamma rays or anomalies in gravitational waves, might one day reveal spacetime's pixelated nature. So is loop quantum gravity the ultimate theory of everything? It's too soon to say. While it elegantly sidesteps singularities and quantizes space, it struggles to explain how the familiar forces like electromagnetism emerge from its framework. Yet its vision of a universe woven from dancing loops offers something profound, a glimpse of reality's deepest architecture, where space and time aren't just backdrops but living, dynamic participants in the cosmic story. If it's right, we're not just living in the universe, we're part of its fabric, threads in an ever-evolving tapestry of existence. Time feels endless, an unbroken river flowing from past to future. But what if it's not? The universe might not just fade into cold darkness. Time itself could one day stop. Picture a future so distant that all stars have burned out, black holes have evaporated, and the cosmos has expanded into an unimaginably vast, lifeless void. This is the big freeze, or heat death, where entropy reaches its maximum and no usable energy remains. In this state, every process grinds to a halt. No chemical reactions, no motion, no change, just an eternal, frozen snapshot where time loses all meaning, because without change, how can time even be measured? But the big freeze isn't the only possible end. Another fate, the Big Crunch, flips the script entirely. If the universe's expansion slows and reverses, perhaps due to dark energy weakening or gravity, finally winning, everything could collapse back into a singularity. Galaxies would rush toward each other, temperatures soar, and space-time itself crumples like a piece of paper tossed into a fire. In this scenario, time wouldn't just stop, it might reverse. Entropy, which normally increases, could begin to decrease, making broken cups reassemble and smoke pour back into candles. The universe would effectively rewind, though whether conscious beings could experience this backward flow is a haunting mystery. Then there's vacuum decay, a far stranger and more sudden end. Imagine the universe's fundamental fields, the invisible scaffolding of reality, are like marbles resting in a valley. They seem stable, but what if there's a deeper valley nearby? A quantum fluctuation could push a tiny region of space into this lower energy state, creating a bubble of true vacuum that expands at light speed. Inside this bubble, the laws of physics rewrite themselves. Atoms disintegrate, space-time warps unpredictably, and time as we know it could simply cease. The unsettling part, this could happen at any moment, with no warning, rewriting existence in an instant. But what if time's end isn't about destruction, but transformation? Some theories suggest that in a universe devoid of energy, quantum fluctuations might still spark new Big Bangs, birthing fresh universes in an endless cycle. Others propose that time's arrow isn't universal, that in some distant, disconnected regions, entropy might decrease, creating pockets where time flows backward. The far future holds even wilder possibilities. If protons decay, as some particle physics models predict, all matter could eventually dissolve into radiation, leaving a universe of light with no structures to mark time's passage. Or perhaps space-time itself, stretched too thin by expansion, fractures into disconnected islands, each drifting alone in an endless sea of nothingness. Will time end? The answer depends on forces we barely understand: dark energy, quantum fields, the very fabric of reality. But one thing's certain, the universe's final act won't be a quiet fade out. It'll be a profound transformation, redefining existence itself. Whether time vanishes, reverses, or reboots, its end will be as enigmatic as its beginning, a reminder that even the most fundamental aspects of reality are anything but permanent. Imagine a clock that ticks forever without ever being wound, a structure that moves in a repeating cycle without any energy input, defying the most fundamental laws of physics as we know them. This isn't science fiction. It's the bizarre reality of time crystals, a strange form of matter that breaks one of nature's most sacred symmetries, the idea that the laws of physics remain unchanged over time. First proposed by Nobel laureate Frank Wilczek in 2012, time crystals don't just exist in space like ordinary crystals, they pulse in time, oscillating between states without any external push, as if the universe itself handed them a perpetual motion machine. How is this possible? Normally, if you set a pendulum swinging, friction will eventually bring it to a stop unless you keep adding energy. But time crystals sidestep this inevitability by existing in a quantum state of constant, self-sustaining motion. Picture a ring of atoms arranged so that their spins tiny quantum magnets flip direction in a never-ending dance. Left alone, without any energy added or lost, this system will keep cycling through its configurations, locking into a rhythm that repeats like the hands of a clock powered by nothing but the universe's own rules. The key lies in what physicists call time symmetry breaking. Just as a traditional crystal breaks spatial symmetry by repeating its structure in space, a time crystal breaks temporal symmetry by repeating its state in time. The implications are staggering. Time crystals challenge the bedrock principle of thermodynamics that disorder always increases, showing that under the right quantum conditions, matter can evade entropy's grip, at least in a limited way. They also hint at new phases of matter beyond the solid, liquid, and gas. We're familiar with phases defined not by spatial arrangements but by patterns in time itself. Think of it like discovering a new dimension of material science, where the fourth dimension isn't just a backdrop but an active ingredient in how substances behave. Where things get really exciting is in quantum computing. Time crystals' resilience to disturbances makes them tantalizing candidates for error-resistant quantum memory. In a quantum computer where fragile qubits can collapse at the slightest interference, a time crystal's stable, repeating state could act as a kind of atomic metronome, keeping operations in sync and shielding information from decoherence. Early experiments with trapped ions and diamond defects have already demonstrated time crystal-like behavior, and researchers are racing to harness their properties for next-generation technologies. But the deepest mystery isn't just how time crystals work, it's what they reveal about the universe. Could they point to undiscovered physical laws hidden in the quantum fabric of reality? Some theorists speculate they might be linked to time's arrow, or even offer clues about exotic phenomena like time loops. For now, time crystals straddle the line between laboratory curiosity and revolutionary breakthrough, a reminder that even the most established laws of physics still hold surprises. They're not just crystals in time, they're crystals of possibility, showing us that the universe's rulebook might have chapters we haven't even begun to read. What if everything around you, the stars, the air you breathe, even the thoughts in your mind, weren't real, but lines of code in an unfathomably advanced simulation? This is the simulation hypothesis, a provocative idea that's moved from sci-fi trope to serious scientific debate. At its core is a startling possibility. Spacetime itself might not be fundamental, but instead a digital construct, like the immersive backdrop of a video game. Think of the universe as a cosmic computer rendering, where what we perceive as reality is just an ultra-high-resolution projection, pixelated at the smallest scales. The argument hinges on a few eerie parallels between physics and computing. Take Planck length, the smallest possible unit of space, about 1/trillionth of a trillionth the width of a hydrogen atom. Below this scale, the concept of distance breaks down, much like how zooming into a digital image reveals individual pixels. Quantum mechanics adds to the intrigue. Particles behave differently when observed, as if the universe is optimizing processing power by only rendering details when needed, like a video game reducing graphics quality in areas the player isn't looking at. Even quantum entanglement, where particles instantly influence each other across vast distances, could mirror data packets linked in a network, updating simultaneously despite physical separation. Philosopher Nick Bostrom formalized this idea with a trilemma. Either civilizations always go extinct before reaching simulation capability, they choose not to create simulations, or we're almost certainly living in one. If advanced civilizations routinely run ancestor simulations, detailed recreations of their past, the number of simulated minds would dwarf biological ones, making it statistically likely we're among the digital ones. Some physicists, like Seeler's Bean, argue that if spacetime is a lattice of discrete points like a grid, high-energy cosmic rays would reveal pixelation effects, anomalies akin to finding the resolution limit of the simulation. Yet critics counter with thermodynamics. Simulating every particle in the universe would require more energy than the universe contains. But proponents suggest shortcuts. Maybe only conscious observers are fully rendered, or the simulation uses lossy compression, skipping unnecessary details. Others point to mathematical elegance in physics. Why would a simulation need beauty, unless, of course, the programmers valued it? The truth is, we may never prove or disprove the hypothesis. But its value lies in the questions it forces us to ask. What is reality? If the universe is code, who wrote it? And if it's a simulation, does that make the stars any less breathtaking or our lives any less meaningful? After all, even if we're lines in a cosmic program, we're lines that can ponder the program itself, and that's a mystery worth unraveling. Neutrinos are the universe's ultimate ghosts, particles so elusive they pass through entire planets like stars through fog. Every second, trillions of them stream through your body, leaving no trace, as if you were nothing but empty space to them. Born in the hearts of stars, supernova, and even Earth's own radioactive decay, these nearly massless particles barely interact with matter, making them cosmic whispers in a world of noise. But their very elusiveness is what makes them revolutionary. Neutrinos might be the key to unlocking secrets Einstein couldn't touch: hidden dimensions, flaws in relativity, or even messages from the far edges of spacetime. Take the case of superluminal neutrinos, a tantalizing anomaly detected in 2011. Scientists at the Opera experiment observed neutrinos apparently traveling faster than light, a finding that, if true, would have shattered Einstein's cosmic speed limit. The result sent shockwaves through physics until it was traced to a faulty fiber optic cable. But what if it hadn't been a mistake? Faster-than-light neutrinos would imply cracks in relativity's foundation, hinting at unknown physics or extra dimensions where particles take shortcuts through spacetime. Some theories, like string theory's brainworld models, suggest neutrinos could occasionally leak into higher dimensions, appearing to break light-speed barriers from our three-dimensional perspective. Then there's the neutrinos' shape-shifting nature. These particles come in three flavors: electron, muon, and tau, and they constantly oscillate between them mid-flight. This bizarre behavior, confirmed by experiments like Japan's Super Kamiokande, proves neutrinos have mass, a revelation that upended the standard model of particle physics. But here's the twist: neutrino oscillations might be sensitive to spacetime's fabric in ways other particles aren't. If spacetime is granular at the quantum level, like a pixelated image, neutrinos could be the pixels we can't otherwise see. Their oscillations might carry imprints of the universe's underlying structure, revealing whether spacetime is smooth or foamy at the smallest scales. Neutrinos also defy expectations by arriving early from cosmic cataclysms. When a star explodes as a supernova, light takes hours to escape the chaos, but neutrinos burst out almost instantly. In 1987, detectors on Earth caught neutrinos from a supernova in the Large Magellanic Cloud 3 hours before telescopes saw the light. This wasn't just a cosmic coincidence, it was proof that neutrinos can slip through matter unaffected, while photons get bogged down. Today, projects like IceCube in Antarctica are turning entire cubic kilometers of ice into neutrino telescopes, hunting for particles from black hole mergers or distant quasars. These ghostly messengers could deliver news from regions of the universe light can't reach, like the cores of active galaxies or the aftermath of the Big Bang itself. Perhaps most intriguing is the possibility that neutrinos are tied to dark matter. Some theories propose sterile neutrinos, a hypothetical fourth flavor that interacts only via gravity, making them a prime dark matter candidate. If these exist, they'd weave through the cosmos unseen, their gravity sculpting galaxies while remaining invisible to our detectors. Experiments like the Fermilab-hosted short baseline neutrino program are racing to find evidence of these shadow particles, which could rewrite our understanding of mass, gravity, and the universe's hidden architecture. So are neutrinos mere cosmic afterthoughts, or the universe's most underrated informants? Their silence is what makes them so powerful. While other particles shout their presence, neutrinos slip through the cracks, carrying secrets from places we can't see and eras we can't revisit. They might be the closest thing we have to messages from beyond space-time, whispers from the dark, waiting to be decoded. Black holes devour everything in their path, but what if the universe has cosmic fountains, gushing out matter and energy instead of trapping it? Enter white holes, the hypothetical twins of black holes, where nothing can enter, only escape. Picture a black hole running in reverse. While a black hole's event horizon is a one-way door to oblivion, a white hole's horizon would be an exit-only chute, violently ejecting everything inside. The math of general relativity allows for such objects, but finding one is another story. White holes emerge from Einstein's equations as a kind of mirror image to black holes. If you rewind the collapse of a black hole, you get an explosion, a singularity bursting outward instead of collapsing inward. Some theorists suggest white holes could be the other side of wormholes, where matter swallowed by a black hole is spewed out somewhere else in the universe, or even in another universe entirely. Imagine a cosmic drainpipe where water, or in this case, stardust, flows in one end and gushes out the other. It's a tantalizing idea, but there's a catch. White holes violate the second law of thermodynamics by decreasing entropy, essentially reversing time's arrow on a cosmic scale. Nature tends to prefer disorder, making white holes seem like mathematical oddities rather than real objects, yet there are intriguing possibilities. Some scientists speculate that the Big Bang itself could have been a white hole event, an eruption of space-time and matter from a singularity. Others propose that tiny, short-lived white holes might explain mysterious cosmic explosions like gamma-ray bursts, where vast amounts of energy appear to materialize out of nowhere. And then there's quantum gravity. If black holes can evaporate via Hawking radiation, could that process somehow bounce into a white hole phase, recycling the black hole's contents back into the universe? The biggest challenge is evidence. Unlike black holes, which leave behind telltale signs like accretion disks and gravitational waves, white holes would be far harder to detect. Their outbursts might resemble supernova or quasars, but without a clear signature, they'd blend into the cosmic noise. Some astronomers have scoured old data for unusual explosions with no apparent source, but so far, no smoking gun. So are white holes real, or just cosmic phantoms, mathematical curiosities with no physical form? For now, they remain a fascinating what if, a reminder that the universe's rulebook might still have pages we haven't read. Whether they're hidden in the distant cosmos or lurking in the equations of quantum gravity, white holes challenge our assumptions about time, entropy, and the very nature of reality itself. Zoom in far enough, past atoms, past quarks, past anything we've ever detected, and you'll reach a scale so small, the very concept of distance starts to unravel. This is the Planck scale, the universe's ultimate resolution limit, where space-time itself might be pixelated. The Planck length, about 1/trillionth of a trillionth the size of a hydrogen atom, is the smallest meaningful unit of distance. Shrink any further, and quantum fluctuations warp spacetime so violently that the idea of here and there loses all meaning. It's like trying to measure the ripples in a boiling pot of water with a ruler. The chaos defies measurement. Time fractures at this scale too. The Planck time, the interval it takes light to cross a Planck length, is a searingly brief 10 to the minus 43 seconds. At this fleeting moment, the ticking of the cosmic clock blurs into a quantum haze. Events shorter than this can't be causally connected. Cause and effect dissolve into a froth of uncertainty. Think of it as the universe's frame rate. Any frames shorter than Planck time would be too jumbled for physics to process. What does this granularity imply? Some theories, like loop quantum gravity, suggest spacetime isn't smooth and continuous but built from indivisible atoms of space, woven together like a cosmic tapestry. These quantum threads could tangle and knot, creating the fabric of reality itself. Other models propose that spacetime at this scale resembles a foamy sea, with tiny bubbles of virtual particles and wormholes blinking in and out of existence. If true, the smooth, curved spacetime Einstein described might just be an illusion, an average of countless quantum flickers, like the calm surface of a lake masking the turmoil beneath. The Planck scale also hints at where Einstein's relativity and quantum mechanics collide. Gravity, which shapes the cosmos on large scales, becomes a quantum force here, fluctuating wildly. Picture a trampoline made of rubber bands, each band snapping and stretching independently, making the surface writhe unpredictably. This is the challenge of quantum gravity, reconciling the orderly geometry of spacetime with the chaotic quantum dance at its foundation. Could we ever probe this realm directly? The energy required to explore the Planck length is staggering quadrillions of times higher than what our most powerful particle colliders can muster. It's like trying to crack a walnut with a galaxy. Yet cosmic rays or primordial black holes might carry clues, and some physicists hunt for subtle anomalies in gravitational waves or light from distant quasars, hoping to catch spacetime's pixelation in action. So is spacetime fundamentally discrete, or is its granularity just a mathematical quirk? The answer could rewrite our understanding of reality, revealing whether the universe is built on a quantum lattice, a froth of bubbles, or something stranger still. One thing's certain, at the Planck scale, the familiar world dissolves into a realm where space and time are no longer the stage. They're part of the quantum performance. Look up at the night sky, and you're seeing only a fraction of the universe. The glittering stars, swirling galaxies, they're just the visible frosting on an invisible cosmic cake. The real scaffolding of the cosmos is made of something we can't see, touch, or directly detect: dark matter. This elusive substance outnumbers regular matter 5 to 1, its gravitational grip shaping everything from the smallest dwarf galaxies to the largest superclusters. Yet despite its overwhelming presence, dark matter remains one of science's greatest mysteries, a ghostly presence that warps space and time while slipping through our detectors unnoticed. Picture the universe as a vast spiderweb with galaxies strung like dewdrops along silken threads. The web itself is dark matter, an invisible network stretching across billions of light years. We know it's there because without its extra gravity, galaxies would fly apart, their stars orbiting so fast that centrifugal force should fling them into the void. This cosmic glue doesn't just hold galaxies together. It bends spacetime itself, creating gravitational lenses that distort the light from distant objects behind it. When astronomers see stretched and duplicated images of faraway quasars, they're witnessing dark matter's fingerprint on the fabric of reality. The strangest part: dark matter seems to play by different rules than everything else we know. Unlike atoms, it doesn't absorb, reflect, or emit light, hence the dark in its name. It barely interacts with normal matter except through gravity, which is why you're currently being passed through by a stream of dark matter particles without noticing. Some theories suggest these could be weakly interacting massive particles that only feel gravity and the weak nuclear force. Others propose actions, ultra-light particles that might transform near strong magnetic fields. Then there's the mind-bending possibility that dark matter isn't particles at all, but primordial black holes formed in the universe's first second. Recent observations add more layers to the mystery. The dark matter halos surrounding galaxies don't behave as predicted. They're less dense at the centers than models suggest. Some dwarf galaxies appear to have almost no dark matter, while others are dominated by it. These anomalies have led to radical proposals like self-interacting dark matter that can collide with itself, or fuzzy dark matter made of wave-like ultralight particles. There's even a controversial theory that dispenses with dark matter entirely, suggesting we've misunderstood gravity at cosmic scales, though most physicists find the evidence for dark matter's gravitational effects too compelling to ignore. The hunt to identify dark matter has spawned extraordinary experiments deep underground, where detectors wait for the once-in-a-lifetime bump of a dark matter particle. In Italy's Gran Sasso Mountain, the Xenon 1T experiment monitors liquid xenon for telltale flashes. In South Dakota's abandoned gold mines, LUX Zeppelin looks for similar signals. These labs are buried to shield them from cosmic rays, filtering out everything but the most elusive interactions. Meanwhile, particle colliders like the LHC attempt to create dark matter in controlled collisions, while space telescopes map its distribution by charting how it warps the light from distant galaxies. Perhaps the most profound implication of dark matter lies in its relationship with time. Because it doesn't interact electromagnetically, dark matter experiences time differently than we do, unaffected by the radiation pressure that shapes normal matter. Some models suggest dark matter could form dark galaxies where time flows at altered rates, or that it might carry information from earlier cosmic epochs we can't otherwise access. Its gravitational influence may even have determined the large-scale structure of the universe in those first critical moments after the Big Bang, setting the stage for everything that followed. What we're glimpsing is a shadow universe, one that exists parallel to our own yet remains just out of reach. Dark matter isn't just some cosmic placeholder, it's the invisible hand that sculpted the universe we know, and may hold clues to dimensions and forces we've yet to imagine. As we peer deeper into this dark mirror, we're not just searching for missing matter, we're trying to read the hidden half of creation's blueprint. Ever noticed how an hour spent scrolling through social media vanishes like smoke, while 60 minutes in a dentist's chair feels like an eternity? Time's passage isn't just governed by clocks, it's sculpted by your brain's quirks. Deep in your hypothalamus, a tiny cluster of neurons called the suprachiasmatic nucleus acts as your body's master clock, syncing with daylight to keep your circadian rhythm ticking. But this biological metronome isn't infallible. When adrenaline floods your system during a car crash, time seems to slow as your brain crams in extrasensory details, creating a high-resolution memory that stretches subjective time like taffy. Dopamine, the brain's reward chemical, plays its own temporal trickery. Novel experiences like traveling somewhere new flood your system with dopamine, which sharpens memory formation. The more densely packed your memories of an event, the longer it feels in retrospect. That's why childhood summers stretch endlessly in recollection, while adult years blur together. Fewer firsts mean fewer temporal landmarks. Psychologists call this the holiday paradox. Time flies in the moment but expands when looking back, all because of how novelty rewires your sense of duration. Even aging warps time's tapestry. As you grow older, each year becomes a smaller fraction of your life. To a 5-year-old, 1 year is 20% of their existence and eternity. To a 50-year-old, it's just 2%, a blink in the rearview mirror. But there's a twist. Mindfulness can stretch time's fabric. Meditation practitioners often report feeling like their sessions last longer than clock time suggests, likely because focused attention heightens temporal awareness, making seconds feel richer. Culture weaves its own threads into this tapestry. Western societies often perceive time linearly, an arrow shot from past to future, while some indigenous cultures view it as cyclical, like seasons repeating. Language itself shapes time perception. Mandarin speakers, who often describe time vertically with up for past and down for future, process temporal sequences differently than English speakers with their horizontal metaphors. The wildest part, your brain might be constructing time's flow entirely. Some neuroscientists argue that consciousness works like a film projector, stitching discrete moments into a seamless narrative. In this view, the now you experience is already a memory, a reconstruction delayed by milliseconds as your brain processes sensory input. Time's continuity could be the ultimate illusion, a trick of perception smoothing over reality's quantum flickers. So is time real or just a story your brain tells itself? The answer might lie somewhere in between, a dance of biology, culture, and attention that bends time's arrow to the mind's whims. One thing's certain, whether it's crawling or racing, time's passage is as much about you as it is about the cosmos. The universe stretches across nearly 100 billion light-years, filled with 2 trillion galaxies, each home to billions of stars. With numbers so vast, the silence is deafening. Where is everybody? This is the Fermi Paradox, the glaring contradiction between the high probability of extraterrestrial civilizations and our complete lack of evidence for them. Even if intelligent life is exceedingly rare, the sheer scale of cosmic time and space suggests we should have stumbled upon something by now. A single civilization, given enough time, could colonize the galaxy in just tens of millions of years, a blink compared to the universe's 13.8 billion-year history. So why does the cosmos feel so empty? One answer lies in the Drake equation, a framework for estimating the number of communicative civilizations. It considers factors like star formation rates, planets' inhabitable zones, and the odds of life arising. Plug in optimistic numbers and the galaxy should teem with civilizations, but use more conservative estimates. Perhaps life is rare or intelligence is a fluke, and the result dwindles to near zero. The equation isn't just math, it's a mirror reflecting our ignorance. We still don't know how life begins, how often intelligence evolves, or how long civilizations survive. Maybe the universe is full of life, but we're all just too far apart in space or time to ever meet. Another possibility is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar travel. It could lurk in our past, like the improbable jump from simple chemistry to self-replicating cells. If this step is astronomically unlikely, we might be among the first, or only, civilizations to make it this far. More unsettling is the idea that the filter lies ahead. Perhaps every advanced civilization eventually destroys itself through war, environmental collapse, or uncontrolled technology. If that's the case, our silence isn't just puzzling, it's a warning. Then there's the zoo hypothesis. Advanced civilizations know we're here but choose not to interfere, observing us like animals in a cosmic preserve. Or maybe they've transcended physical space entirely, uploading their minds into digital realms or higher dimensions we can't perceive. If a civilization masters nanotechnology or harnesses black holes for energy, their presence might be invisible to our primitive senses. They could be all around us, encoded in the fabric of spacetime, communicating in ways we can't yet fathom. The darkest answer is that we're alone. The universe might be a vast desert with Earth as its sole oasis. All life could be common, but intelligence is a dead end, an evolutionary accident that flickers out before it can spread. Either way, the silence forces us to confront our place in the cosmos. Are we the universe's firstborn, its last hope, or just a fleeting spark in an indifferent void? Until we find proof, the question lingers haunting, humbling, and utterly unresolved. In the first trillionth of a trillionth of a trillionth of a second after the Big Bang, the universe did something extraordinary. It didn't just expand, it exploded. ballooning from smaller than an atom to the size of a grapefruit in a fraction of a blink. This wasn't ordinary expansion. It was cosmic inflation, a runaway growth spurt that stretched spacetime itself faster than light could chase it. Picture a speck of dust suddenly swelling to the size of the solar system before you could snap your fingers. That's the staggering speed of inflation, and it's the reason the universe looks the way it does today. Inflation solves mysteries that once baffled cosmologists. Take the horizon problem. If you look at opposite ends of the night sky, those regions are so far apart that light hasn't had time to travel between them since the Big Bang. Yet they're nearly identical in temperature, like two strangers on different continents wearing the same outfit. How inflation stretches a tiny, uniform patch of spacetime across the entire observable universe, preserving that sameness like a cosmic photocopier. Then there's the flatness problem. The universe's geometry is eerily precise, like a pencil balanced on its tip for billions of years. Inflation's hyper-stretching ironed out any primordial wrinkles, leaving spacetime so flat that even the slightest curvature would have torn the cosmos apart long ago. What could have powered such violent expansion? The leading suspect is a hypothetical quantum field called the inflaton, a sort of cosmic adrenaline rush. As this field decayed from a high-energy state, it released torrents of repulsive gravity, pushing space apart from the inside. Think of it like a ball rolling down a hill, except the hill was made of anti-gravity, and the ball was space-time itself. When the inflaton finally settled, its energy didn't vanish. It transformed into the matter and radiation that filled the young universe, lighting the fuse for the Big Bang's afterglow. But here's the twist: inflation might not have been a one-time event. Some theories suggest it's eternal, with pocket universes endlessly budding off like bubbles in a never-boiling pot. Our observable cosmos could be just one bubble among countless others, each with its own laws of physics. In this wild scenario, inflation didn't just shape our universe, it's still happening somewhere, right now, birthing new realities beyond our cosmic horizon. The echoes of inflation are still with us today, etched into the cosmic microwave background like fingerprints on a frozen window. Tiny quantum fluctuations during that explosive stretch were blown up to cosmic scales, becoming the seeds for galaxies and galactic clusters. Without those microscopic ripples, gravity would have had nothing to grip, and the universe would have remained a featureless void. Inflation didn't just stretch space, it planted the blueprint for everything that followed, from the first stars to the spiral arms of the Milky Way. Yet for all its explanatory power, inflation raises new questions. Did it start everywhere at once, or was it triggered in some regions but not others? Could there be corners of the cosmos where inflation never stopped, stretching space into an infinite expanse beyond our view? The answers might lie in gravitational waves from the universe's first moments, subtle ripples that future telescopes could detect. Until then, inflation remains the best story we have for how nothing became everything, a fleeting instant that set the stage for all of spacetime's wonders. From the quantum foam to the cosmic web, space and time have revealed themselves to be far stranger than our ancestors could have dreamed. What once seemed like an empty stage for matter and energy is now understood as a dynamic, living fabric, one that bends, ripples, and even pixelates under extreme scrutiny. We've ventured through warped spacetime near black holes, where gravity twists reality into knots, and peered into the quantum realm, where particles flicker in and out of existence like cosmic fireflies. We've grappled with theories that suggest multiple universes might bubble up beyond our own, each with its own laws of physics, and pondered whether our entire reality could be a holographic projection encoded on some distant boundary of the cosmos. Yet for all we've uncovered, every answer seems to birth new questions. The mysteries of dark matter and dark energy remind us that most of the universe remains hidden from view, while the paradoxes of quantum mechanics and relativity whisper of deeper layers waiting to be peeled back. Even time itself, the steady tick of our daily lives, turns out to be elastic, stretching and compressing depending on gravity and motion. The more we learn, the clearer it becomes that space and time aren't just backdrops to existence. They're active players in the universe's grand story, shaping everything from the birth of stars to the flow of our own consciousness. What's next? The frontiers of physics are alive with possibility. Gravitational wave astronomy is opening a new window onto cosmic collisions, while quantum computers might soon simulate conditions we can't recreate in labs. Theories like loop quantum gravity and string theory continue to push the boundaries of our imagination, suggesting that spacetime itself could emerge from something even more fundamental, a cosmic code we've yet to crack. And who knows, the next great discovery might come from an unexpected corner, rewriting the rules once again. So as we stand on the shore of this vast ocean of unknowns, let's keep our curiosity alive. The universe isn't just a puzzle to be solved, it's an endless invitation to wonder. Whether you're gazing at the night sky, pondering the nature of time, or simply marveling at the fact that you're made of stardust, remember, every question asked, every experiment run, brings us closer to understanding our place in this breathtaking space-time tapestry. The journey isn't over, it's just beginning.